All right. Um, Now, this is the one-way shear, and the capacity for solving the one-way shear is given by this equation. Now, as I've said earlier, that we'll also have to compare the capacity to the loads, to the load sides. Now, the loadings, it's given by these equations of V, that's the ultimate or factored loads, V sub U is equal to the factored soil pressure times B times this distance. Okay, so L over 2 plus C over 2 minus D. By the way, I think this is positive. Okay, so this one is the load side, and this one is the resistance side. Now, this Q, this is the factored soil capacity. So since this is a shear force, then meaning that we can obtain the force from the stresses, or let's say the pressures, and the area. So this is just basically the area, let's say the portioned area. So meaning B, that's this width. So this is B times this distance. Okay, so if you look at this pictorial view, it's actually this shaded area at the bottom. It is actually a rectangular area. Okay, so meaning that's gonna be the shear force at that portion. Now, to solve for D, we just have to equate the two equations, meaning that VC is equal to V sub U. Now, if you equate the equations, uh, the unknown that's left would be the this letter D. Okay, so the same goes through here. So just a couple of notes when you are computing for this, just make sure that this one is in mm, because at first you might be using the units in meter for the beam width, since our given pressures is in kilopascals. So you have to convert that to mm, and then this FC prime is in megapascals. That's in Newton per mm squared, and we have these factors. The value of the strength reduction factor is just, since this is shear, then this is 0.75. Okay, so on the right side, we have this Q, U. This is the factored soil pressure. So since at first you'll have the units in kPa, and you have to convert that to, so convert that to megapascals, MPa, and this one would be in, again, this area should be in mm squared. Okay, so once you equate that and then you solve in the calculator, my advice is to is to use the shift solve function, and it can save you a lot of time, and it will give you a value of D. So for now, since there's one value of D for a one-way shear, then we'll just label that as D sub 1. There's another value that will obtain when we're dealing with a two-way shear. Okay, so for a two-way shear, it's actually like this. So the two-way shear, also referred as a punching shear, then basically at some distance here, or at some critical section, actually this portion is punching through the footings. Okay, so what is that distance? Now, if you look at the top view, this is our column, and the column with, let's say it's C. we designate that as C. Then the distance from the face to another to this point, to this critical section, that's D all over 2. On the other side, that's still the same, D over 2. And if you check the other side here, that's still D over 2. But since we're just dealing with square footings and square columns, then it's just gonna be the same. Now this critical section, we're going to need this parameter, and that's actually the perimeter of this critical section. So how do you find the perimeter of the section? It's basically D over 2 plus C plus D over 2. So since this is square, then you just multiply that by 4, and that's gonna be our perimeter. Now for the capacity of concrete, it's actually given in 3 conditions. So the first one is phi times 1/6 of 1 plus 2 over beta times the lambda and then the square root of fc prime times b sub o d. So that's the first condition. The second condition is 112 times this alpha sub s times d over b sub o plus 2 times alpha, then square root of fc prime, then b sub o times d. And then the third condition, fc prime b sub o times d. Basically, in our computations later on, we'll just use this criteria. But to have an overview about these equations, this beta is just simply this is the ratio of the long side to the short side. So that's going to be the criteria if we have a rectangular, let's say we have a rectangular footing cross section. So that's the beta. And for this one usually governs if the beta is less than or equal to 2. But if beta is greater than 2, then this one typically governs. But you have to check that out. By the way, this one is this alpha s. Actually, this refers to the location of the footing. Now, for example, we have, okay, so for the first one, let's say we have a concentric footing, then our alpha is 40. Okay, so this value can be found in our lecture handouts, and that's 10-4, table 10-4, and this is interior column. Now for the edge, meaning you have this column at the edge, along the edge, then this alpha s is 30. And if you have a corner column, then this alpha s is equal to 20. Okay, so you can just count the sides. Let's say for this corner, so you have 1, 2, so you have this 20, and then for this edge 1, 2, 3, then for the interior 1, 2, 3, 4. Okay, so anyways, we'll focus only on this criteria. Now we have this reduction factor, and since this is shear, then that's going to be 0.75, and this one is the concrete modification factor, and as I've said, this alpha is equal to 1 for normal weight concrete. So unless otherwise specified in our calculations or homeworks, then we'll just have to use this alpha is equal to 1. This fc prime is the compressive strength of concrete, and this one, okay, so b sub o, so you can just call it like B naught. So B naught is actually the perimeter at the critical section. So this is it. Okay, so what is this perimeter? So for square, it's just simply the sum of the four sides. So that can be simplified as 4c plus d, or 4c plus 4d if you distribute this. Now for the load side, the factored load is equal to the factored soil pressure times the area. So what is the area? What is this shaded area? Basically, since this is square, then the area of this outer square, or let's say this largest square. So let's say this is B. So meaning that's going to be B squared minus the area of this critical section. Okay, so since this is our length on one side, the length of the critical section, so it's just basically C plus D. So meaning it's gonna be C plus D and square it. Okay, so that's gonna be our equations for the two-way shear. Now to solve for D, then you have to equate again the factored shear capacity to the factored loads, and then again you just have to check the units. So if this is in millimeters, then this one should be in megapascals, and also the left hand sides. So this one should be in millimeters and this one in megapascals. Okay, and again you can just do the shift solve function of the calculator and be able to obtain the value for the D. Now this is going to be our D sub 2. So meaning we have already two values of D. Now which D are we going to use? So the D would be the maximum of D1 and D2, whichever gives the greatest, then that's going to be our D. Alright, so enough for the shear. Now let's discuss the flexural strength of the footing. Now this is our footing, and when it's subjected to loads, and let's say the pressure is also here, one tendency or another tendency is to have a bending of this let's say of this portion. Okay, so we have a bending here. So if there's going to be a bending, then we know that in flexure there's actually tensile stresses and compressive stresses, so we have to reinforce the tension zone. This is actually typical or the same with the I think that's the sign of let's say singly reinforced beams with known cross sections. Okay, so meaning that you have already the dimensions of the footing, but then you have to provide the required steel area. Okay, so let's say if we draw it like this, so if it bends this way, then there's gonna be reinforcement here. Okay, so if we try to look at that in this view, our reinforcement is along this direction. Now it's also possible, or it's actually also occurring on the other side. So So if we consider the bending on the other side, okay, so let's say we consider the bending on, let's say, on the other side, so meaning that we have also to provide reinforcement along this direction. So now if we try to look at the top view or the plan view, you'll see that there's going to be bars on this way, on this direction, and there's going to be bars on this direction. Now for a square column, then the distribution of bars will be the same. But for a rectangular, I mean, uh, not column, I mean the footings. But for a rectangular footings, then there's going to be a different direction along this, let's say the long side. So it has some more extra computations for this because it's not actually the same all throughout the length. Anyways, since we're just dealing with a square footing, then we'll just have the uniform spacing. Okay, so again, as I have mentioned, that the flexural strength, we can relate that to the actually to the design of, um, or let's say design, or actually, or we can say calculate the steel area, the required steel area. So since it's a design, then given the loads, based on the loadings, what's going to be the steel area? Okay, so how do we compute that? So recall that we have this expression that the factored capacity is equal to, or must be greater than or equal to the factored loads. Now, if we solve this, um, if we solve this load sides, actually we can determine this load side. Now, if you have this and you assume a reduction factor, let's say a tension controlled, then you can actually obtain the nominal capacity. Now, once you have the nominal capacity, then you can actually solve for rho, for the steel area. So given by this equation 0.85 Fc prime over Fy, this one we didn't solve this. We didn't solve any problem using these equations, but I think I did mention this in our lecture in singly reinforced beams regarding the steel ratio is 1 minus 2 mn. Okay, so phi times 0.85 Fc prime times BD squared. Okay, so that's the equation. Okay, so once you have this, then you can solve for the steel area. So AS is just rho BD. So I guess we'll just stop in this topic section up to flexural strength, and then we'll do a sample problem up to the flexural strength. Then if we still have time, then we'll continue our discussion on the development length and the bearing capacity of the footing. Okay, so for now our calculation will be up to the flexural strength only. Alright, our first problem will be taken from the book of Engineer Gilisania. So this will be our reference text for this topic, the reinforced concrete design, simplified, 2010 NSCP. Now in this page, there's actually a Okay, so this is actually the problem. So it says here that a square column footing is to support a 500 square tied column that carries service dead load of 1,200 kilonewton and service live load of 1,100 kilonewton, 120 kilonewton. The column is reinforced with 8 25 diameter bars. The base of the footing is 1.5 meters below the natural grade, where the allowable soil pressure is 310 kilopascals. The soil above the footing has unit weight of 15.6. Assume Fy is equal to 275 megapascal, and Fc prime equals 27.5 megapascals, and unit weight of concrete as 23.5 kilopascals. Now design the footing using 25 main bars and 75 clear cover. Now this one says that we are going to use the 2001 SCP, but another problem, the problem 6.2, says that we're going to use the 2010 NSCP. Alright, so now if we try to draw it here in our paper, then this will be the illustration of the problem. So it says here that from the natural grade line we have 1.5 meters, and our column is 0.5 meters, and our dead load is 1,200 kilonewton, and this one is 1,000. The live load is 1,120 kilonewton. Now it says here that it's going to be designed as a square footing, and the details, the data, will be this. Now to solve, I've also included in our lecture handouts the procedure, and you can also follow that one. Now, so for the first part, we'll solve. Actually, we have to establish the dimensions of the footings. Okay, so let's first solve for the effective soil bearing pressure. How the equation would be Q sub E is equal to the allowable minus the unit weight of, let's say, the concrete plus times the height of concrete, and plus the unit weight of soil times the height of the soil above. Okay, so we cannot have this height of concrete since it's not yet given. But the typical approach in solving this problem is to assume a height of concrete, and then later on we'll just check if the computed value of D plus the concrete cover and other details, if it's greater than or equal to this. So if it fails, then we have to redo the calculations. Now in the text it says that the assumption is that the height of concrete is equal to 0.8 meters. So therefore, the height of the soil, okay, so if this is 0.8 meters minus this, or 1.5 minus 0.8, then what's left is the height of soil, which is 0.7 meters. Okay, so if we solve this, we have 310 kilopascals minus the unit weight of concrete, which is 23.5 times the height, 0.8, okay, plus the unit weight of soil, 15.6 times the height of soil, which is 0.7. And this one, the unit of this is in, so this is in kilonewton per meter cube times meters. So that's going to be kPa. Now if you solve this, you get a value of 280.28 kPa. Okay, so if you try to illustrate this, this is our footing, and then this is our column. So recall that in our discussions that um, we have this soil pressure, effective soil pressure, by considering the unit weights of the concrete plus the unit weight of soil, so PC, and then our unit weight for the soil. So that's it. Now, if we since we have the effective um, since we have now the effective soil pressure, then we can solve for the footing area, for footing area. Okay, so A is just simply the unfactored loads, AD plus L all over the Q effective, and that's going to be 1,200 plus 1,120 all over 280.28. Now, if you solve this, what you get is 8.28 meter squared. Okay, so this is our area. Now, since we have the area, then we can solve for the beam width. So let's say the B. So B, actually, the area is just basically side times side. So B squared is equal to A. So B is equal to the square root of A. And if you substitute this value, what you get is 2.87 meters. Okay, so you round that up um, to a practical value, let's say 2.9 meters. Okay, so meaning that our our column is like this. So we have it 2.9 meters by 2.9, and then this one is 0.5. This is 0.5 for the column width. Right, so now the next step is to, let's say, solve for factored soil pressure. Okay, so our factored soil pressure is Q sub U is equal to, that's the factored loads divided by the actual area. Okay, so what is this factored loads? We have a loading combination of 1.2 dead plus 1.6 live divided by the actual. So the actual is 2.9 times 2.9, and if you substitute the value, you get a 384.3 kilo pascals. Now, if you convert this to megapascals, you have to divide that by 1,000. Okay, so if you divide it by 1,000, you get 0.384 megapascals. Okay, so now we're good to go. We have to check now the shear. We have to determine the footing thickness based on the two shear conditions. Okay, so let's say this is our major step number 2. This is major step number 1. Okay, so determining footing thickness based on, let's say, one-way shear. Okay, so we have to draw first, and since this is square, then we can just select any size here. and we can solve for the critical section. So it says that for one-way shear, we have a critical section at a distance d, okay, from the face of the column. So meaning from this face to this, that's the distance d, and this will be the critical section. Okay, so this one is 0.5, and then this one is 0, I think this is 0, not 0, this is 2.9, and our beam width is, okay, let's say this is our B, this is the same 2.9, and this one is our L. So meaning that our distance here, the distance is just equal to L over 2 plus C over 2 minus minus D. Right, I think we'll continue this discussion in the next video.